but tuning requires patience due to how the elements interact with one another. The wires must be physically separated to minimize capacitive coupling. If installed horizontally or as an inverted V, you spread the ends out like a cat's whiskers. If the wires must run parallel, use PVC or lightweight fiberglass spacers to keep them at least 4 to 6 inches apart. Always cut your wires a few inches longer to leave room for tuning. Start by transmitting on the lowest frequency band, that is 80 meter, and pruning the longest element for the lowest SWR. Once the 80 meter element is tuned, move to the 40 meter element. Here is the catch. Trimming a shorter element. The term cat's whisker dipole is a colloquial name for a fan dipole or parallel multi-band dipole. It is an incredibly efficient, low-cost way to operate on multiple HF bands using a single coaxial feed line, avoiding the losses and bandwidth restrictions of traps or the need for a remote antenna tuner. A cat's whisker consists of multiple half-wave dipoles cut for different bands, all joined in parallel at a single center insulator or 1:1 balun. When you transmit, no physical switching is required. The RF energy automatically seeks the path of least resistance. The dipole element that is resonant at your transmission frequency will present a very low impedance, typically around 50 to 70 ohms, while the non-resonant elements will present a very high impedance. The RF naturally flows almost entirely into the resonant element. If you want to cover 5 bands such as 80 meter, 40 meter, 20 meter, 15 meter and 10 meter, you only need 4 sets of wires. This is because a dipole naturally resonates on its odd harmonics. The 40 meter element will act as a 3/2 lambda dipole on 15 meter, giving you that 5th band for free. Here are the approximate starting lengths for each leg of the dipole. 80 meter around 19.3 meter, 40 meter and 15 meter element 10.1 meters, 20 meter element about 5 meters and 10 meter element about 2.5 meters. Building the antenna is straightforward, but tuning requires patience due to how the elements interact with one another. The wires must be physically separated to minimize capacitive coupling. If installed horizontally or as an inverted V, you spread the ends out like a cat's whiskers. If the wires must run parallel, use PVC or lightweight fiberglass spacers to keep them at least 4 to 6 inches apart. Always cut your wires a few inches longer to leave room for tuning. Start by transmitting on the lowest frequency band, that is 80 meter, and pruning the longest element for the lowest SWR. Once the 80 meter element is tuned, move to the 40 meter element. Here is the catch. Trimming a shorter element will slightly shift the tuning of the longer ones. You will usually need to iterate through the bands 2 or 3 times until the SWR is acceptable across the board. While you can feed a cat's whisker directly with coax, using a 1:1 current balun at the feed point is highly recommended. It prevents common mode currents from traveling back down the coax shield, keeping RF out of your shack. The IO antenna is a lightweight dual band VHF-VHF portable directional antenna designed specifically for working low Earth orbit FM satellites with a handheld transceiver. Designed by Spanish radio amateurs EA4CYQ and EB4DKA, it has become a popular homebrew alternative to commercial satellite antennas because it is incredibly cheap to build and easy to pack flat for portable operations. If you look closely at the schematic, The antenna relies on cubical cord principles using a driven square loop and a single linear reflector for each band. The name IOIO isn't an acronym, it is a visual representation of the antenna's elements as they sit on the boom. Capital I and O, the large VHF linear reflector I and the large VHF square loop radiator O. Small letter I and O, the smaller UHF linear reflector small I and the smaller UHF square loop radiator small o. The antenna is actually an evolution of their earlier single band 70 cm design called the canary jail umbrella, named because the original prototype was built using a plastic tube taken from a canary cage and metal ribs salvaged from a broken umbrella. Why choose the IOIO? For LEO satellite tracking, the standard choice is often a commercial arrow antenna or a homebrew tape measure Yagi. However, the IOIO offers a distinct mechanical advantage. It is entirely two-dimensional. Because a standard dual-band arrow antenna uses crossed Yagis, elements oriented 90 degrees apart, it is bulky and takes several minutes to assemble in the field. The IOIO's loop and straight reflectors all lay flat on a single plane. You can easily slide it behind a car seat, lay it flat in a trunk, or pack it in a suitable case without taking it apart. Here is how it stacks up against a traditional crossed Yagi design. Element design of IOIO antenna is square loops and straight reflectors, while it is linear dipoles for typical crossed Yagi. Physical profile two-dimensional, lays flat in case of IOIO antenna, while typical crossed Yagi has three-dimensional elements at 90 degrees angles. UHF gain equivalent to a 4-element Yagi in case of IOIO antenna, equivalent to a 7-element Yagi for typical crossed Yagi. Portability excellent, ready to use instantly in case of IOIO antenna, while it is good for typical crossed Yagi, requires breakdown to pack flat. While it gives up a little bit of gain compared to a longer 7-element UHF Yagi, it still provides a generous beam width and plenty of signal to comfortably pull the modulation out of the noise on passes from birds like SO50 or the ISS. The canary jail umbrella or CJU antenna is an ultra-compact directional 70 cm, that is 435 MHz UHF antenna designed specifically for low Earth orbit amateur satellite communications. Created in 2006 by Spanish amateur radio operator Echo Alpha 4 Charlie Yankee Quebec, it gained widespread popularity in the satellite community for delivering high sensitivity and directivity in a pocket-sized form factor. The whimsical name comes directly from the makeshift household materials Echo Alpha 4 Charlie Yankee Quebec used to build the original prototype. His father, Echo Alpha 4 Alpha Bravo Victor, suggested using a non-conductive plastic perch salvaged from a pet canary cage as the antenna boom. Echo Alpha 4 Charlie Yankee Quebec recovered steel ribs from a discarded broken umbrella found in a trash bin to fashion the driven and reflector elements. When he tested the prototype with fellow satellite enthusiast Echo Bravo 4 Delta Kilo Alpha, the comical origin led Echo Bravo 4 Delta Kilo Alpha to christen it the canary jail umbrella antenna. The CJU is a modified 2-element parasitic array optimized for UHF satellite downlink reception. Rectangular driven element or radiator. A closed rectangular wire loop approximately 230 mm wide by 107 mm high, bent from 2 mm steel rod. It functions similarly to an oblong quad loop, exhibiting a feed point impedance near 50 ohms without requiring complex matching steps, gamma matches or balance. Linear reflector. A straight rod approximately 338 mm long, positioned approximately 50 mm behind the driven element to provide forward directivity and ray attenuation. Integrated connector. The base of the non-metallic boom attaches directly to a BNC plug via a short internal jumper like RG223 or RG58, enabling the antenna to mount straight onto a handheld transceiver. Here are the details. Band 70 cm amateur UHF satellite subband 435 to 438 MHz. Configuration 2 element rectangular loop driver and linear reflector. Gain around 5 to 6 dBi. Feed point impedance direct 50 ohm match. Low SWR across 435 to 438 MHz. Total boom length less than 20 cm. Mounting direct BNC mount to handheld transceiver top panel. Why it excelled for satellite operations? Eliminates feedline loss. At 435 MHz, standard RG58 jumper cables can easily lose 1 to 2 decibels of weak satellite signals. Mounting the CJU directly onto the handheld transceiver BNC socket virtually eliminates coax attenuation. Dynamic polarization tracking. LEO satellites tumble and experience Faraday rotation, causing rapid polarization shifts. Because the entire HT and antenna are held in one hand, the operator can continuously match polarization simply by twisting their wrist. Minimal weight and footprint. Unlike multi-element arrow or ELK log periodic antennas that require two handheld manipulation or heavy booms, the CJU weighs only a few tens of grams and fits inside a coat pocket. Popular derivatives. IO-IO antenna. EFO CYQ expanded the CJU concept into a dual band 2 meter VHF, 70 cm UHF handheld satellite antenna. Viewed from the side, the element arrangement resembles the letters capital IO and small letter IO. 2 meter linear reflector capital I, 2 meter loop driver capital O, 70 cm linear reflector small letter I, and 70 cm loop driver small letter O. JAC1 CPA 3 element modifications. Japanese amateur radio experimenter JA1 CPA optimized the CJU design with added directors and refined coax feed trimming, achieving directional gains exceeding 9 dBi. The Swiss Quad is a highly efficient directional loop antenna developed in 1960 by Swiss amateur radio operator HB9CV. It is a unique variation of the traditional cubical cord that solves some of the mechanical fragility of the original design while also altering its electrical properties to improve performance. A conventional two-element cubical cord uses one driven element and one parasitic element, a reflector or director, supported by an X-shaped frame of fiberglass or bamboo spreaders attached to a horizontal boom. The Swiss cord throws out both the boom and the spreaders. Unlike a standard quad, both elements in a Swiss cord are driven. It is effectively a folded loop version of the famous HB9CV phased array. The two loops are fed with a phase difference of approximately 180 degrees, usually via a double gamma match or T match. This phased feeding creates a highly directional pattern with a very deep null off the back of the antenna. Instead of using non-conductive spreaders, the horizontal top and bottom sections of the loops are made of rigid metal tubing, usually aluminum or copper. The centers of these horizontal tubes are bent inwards at a 45-degree angle until they meet at the central vertical support mast. Because the exact center of a driven quad loop sits at 0 RF potential, these metal arms can be bolted directly to the grounded mast without requiring insulators. For HF bands, the vertical sides of the loop are simply made of wire strung between the rigid top and bottom tubes. For VHF-UHF bands, the entire structure is often made of tubing. Advantages: superior sturdiness. By eliminating the boom and the large flexible X spreaders, the Swiss cord is mechanically much stronger and handles wind loads far better than a traditional quad. Better gain. The dual-driven phased elements provide slightly more forward gain than a standard parasitic 2-element cord, performing closer to a 3-element Yagi. High front-to-back ratio. The phasing creates excellent rejection of signals coming from the rear, making it highly effective for rejecting QRM interference. DC grounded. Because the elements are physically clamped to the grounded mast, the entire antenna sits at DC ground. This bleeds off precipitation static, resulting in a significantly lower noise flow on reception and offers better lightning protection. Because of the physical size of the horizontal metal tubing required, Swiss cords are most popular on VHF, that is 2 meter and 6 meter, and the higher HF bands 10 meter, 12 meter and 15 meter. An LFA or loop fed array Yagi is a highly specialized directional antenna designed specifically to deliver an extremely low noise floor. Developed by antenna designer Golf Oscar Kilo Sierra Charlie, it is primarily used in amateur radio for weak signal work. While it looks largely similar to a standard Yagi-Uda antenna, its defining feature is its driven element, the part where the transmission line connects. Instead of a simple straight rod or dipole, the LFA uses a flat, closed rectangular loop. The magic of the LFA lies in the specific shape and phasing of that rectangular loop. The broad sides, the long sections of the loop run parallel to the other parasitic elements. These do the actual radiating and receiving in the forward direction. The end sections, the short sides of the loop run parallel to the central boom. Because of the loop's precise dimensions, the electrical currents flowing through these two short end segments are exactly 180 degrees out of phase with one another. Phase cancellation. When currents are out of phase, their electromagnetic fields cancel each other out. This effectively acts as a spatial filter, drastically shrinking the antenna's side lobes, its sensitivity to signals coming from the sides, top and bottom. Key advantages: exceptional noise rejection. By suppressing side and rear lobes, the LFA Yagi ignores much of the man-made electrical noise, that is QRM, common in urban environments such as power line noise and electronic interference. Better signal-to-noise ratio or SNR. Because the background noise flow is physically blocked from entering the receiver, incredibly faint signals that would normally be buried in static become perfectly readable. Direct 50 ohm match. Many LFA designs naturally present a 50 ohm impedance at the feed point. This means they can be connected directly to standard coaxial cable without needing complex or lossy matching networks like hairpin matches or gamma matches that standard Yagis often require. Because of their noise rejecting properties, LFA Yagis are highly priced on VHF and UHF bands like 6 meters and 2 meters for extreme weak signal propagation modes including Earth-Moon-Earth or moonbounds, meteoscatter, and tropospheric ducting. A linear loaded dipole is a type of shortened antenna where a portion of the radiating element is folded back on itself to create a shortened transmission line stub. This fold adds the necessary inductive reactance to electrically lengthen the antenna without requiring the massive physical footprint of a full-size half-wave dipole. If you are trying to make an existing 80-meter dipole resonate on the 160-meter band without increasing its total physical length or shifting the feed point, linear loading is arguably the most efficient way to achieve it. When you fold the wire back parallel to the main element, the parallel section acts like a shortened transmission line stub rather than a pure radiator. This stub introduces inductance to the antenna system. Unlike a traditional loading coil, which concentrates the inductance in one localized spot, linear loading distributes this inductance along a section of the antenna. For homebrewing antennas, especially when running external power like linear amplifier, linear loading offers distinct advantages over traditional base or center loading coils. Efficiency Q factor. High for linear loading, lower resistive losses because the inductance is created by continuous thick antenna wire. For coil that is inductive loading, it is lower. Coils introduce resistive losses which turn your RF output into heat. Bandwidth. Broader for linear loading, maintains a slightly wider usable SWR curve across the band. Narrow for coil loading. High Q coils create a sharp resonance, often requiring a tuner for small frequency shifts. Power handling is excellent for linear loading, handled entirely by the wire gauge, no risk of arcing between tight coil windings. Power handling is limited for coils. Coils can overheat, melt, or arc if not heavily built for the amplifier's output. Construction is mechanically complex for linear loading, requires a rigid spreaders like PVC conduit to keep the wires parallel and evenly spaced in the wind. While for coil it is mechanically simple, just insert a wound inductor in line with the wire. To build or modify one, the parallel wires must be kept perfectly separated to function correctly. Spreaders. Use lightweight, non-conductive material like CPVC pipes, fiberglass rods, or even electric fence insulators. Drill holes to route the wire through. Spacing. The exact spacing between the parallel wires isn't hypercritical for resonance, but consistency is vital. A gap of 2 to 4 inches is standard for HF bands. Wire routing. The wire goes out from the feed point, passes through the spreaders, turns back at a specific length, routes backward towards the center, and then turns again to extend outward for the rest of the antenna leg. The ladder line hack. Instead of dealing with individual wires and custom spreaders, many builders use a length of 300 ohm or 450 ohm twin lead or ladder line for the folded section, shorting the ends as required to create the stub. Calculating the exact wire lengths for a linear loaded dipole is more complex than a standard dipole because the folded parallel wires act as a shorted transmission line, introducing distributed inductance. If your goal is to build this 160 meter antenna without increasing the total physical span beyond the footprint of a standard 80 meter dipole, that is approximately 130 feet total or 65 feet per leg, you will need to rely on a 3-wire fold to achieve resonance within that restricted space. Here is how to calculate the dimensions. First, calculate the full size of a standard half-wave dipole for your target frequency, example 1.85 MHz. Please note that VU 160 meter band is only up to 1.825 MHz. A common formula for length of a dipole in feet is 468 divided by the frequency in megahertz. So that will come to around 253 feet. This means a full-size 160 meter dipole requires roughly 126.5 feet of physical space per leg. By keeping the antenna confined to roughly 65 feet per leg, you are physically missing about 61.5 feet of wire reach on each side. You cannot simply fold 61.5 feet of wire back into the available space to make up the difference. When you fold the wire back parallel to itself, it forms a shortened transmission line stub. This generates distributed inductive reactance XL, which electrically lengthens the antenna. The inductive reactance provided by a shorted stub of length L is calculated as XL is equal to Z0 tan of 2 pi L by lambda, where Z0 is the characteristic impedance of the parallel wires determined by wire thickness and the spacing of your spreaders. L is the physical length of the folded section. Lambda is the wavelength. Because this shortened stub acts as an inductor, the actual length of wire needed in the folded section is slightly less than the straight mathematical missing length. Because calculating exact distributed capacitance and Z0 in an open air wire array is highly complex and sensitive to environmental factors, it is best to use established reduction ratios. The linear loading method effectively folds the dipole elements back on themselves. 2-wire fold. With a 2-wire loaded dipole, the resonant frequency is reduced to about 0.67 to 0.70 of a standard dipole of the exact same physical length. This would reduce a 160 meter antenna to a physical footprint of roughly 85 feet per leg, which is still too long to fit an 80 meter dipole footprint. 3-wire fold. With a 3-wire loaded dipole, the resonant frequency is reduced to about 0.55 to 0.60 of the reference dipole of the same length. A reduction to 55% brings the physical length reach of our 160 meter dipole down to roughly 69 feet per leg, which closely matches your spatial limit. To achieve resonance within a 65-foot physical leg, use the following starting measurements. Total wire, start with approximately 105 feet of continuous wire per leg. The first run the wire from the center feed point outward for 25 feet. The fold the wire back towards the feed point for 20 feet, threading it through non-conductive spreaders to maintain a consistent 2 to 4 inch spacing. The extension. Fold the wire outward one final time and run the remaining 60 feet out to your end insulator. The geometry check. This puts your final end insulator exactly 65 feet from the feed point, that is 25 feet out minus 20 feet back plus 60 feet extension is equal to 65 feet physical reach. Factors like proximity to ground and other nearby objects have significant impact on the actual tuned length. So you should always make the prototype antenna slightly longer than calculated. Leave an extra 2 to 3 feet of wire at the far end of the extension, folding it back on itself so you can trim the antenna while measuring its performance with an analyzer to find perfect resonance. A balanced modulator is an electronic circuit that mixes two signals, typically an audio signal and a high-frequency radio carrier, to produce a double sideband suppressed carrier signal. In standard amplitude modulation, a massive amount of transmitter power is wasted broadcasting the carrier wave, which contains no actual information. A balanced modulator solves this by mathematically multiplying the two signals and cancelling out the carrier, leaving only the information carrying sidebands. A balanced modulator takes two inputs. One, the modulating signal, the information you want to transmit, like a voice audio wave. Two, the carrier signal, a continuous high-frequency radio wave generated by an oscillator. The circuit is designed with a symmetrical, that is balanced layout using non-linear components like diodes or transistors. When the carrier is fed into this symmetrical bridge, it is split into two equal but opposite currents that cancel each other out at the output transformer. Because the carrier is suppressed, the output consists entirely of the sum and difference of the two input frequencies. Upper sideband is carrier frequency plus modulating frequency. Lower sideband, carrier frequency minus modulating frequency. The balanced modulator is the critical first step in modern voice radio communications, specifically in generating single sideband signals. Because the balanced modulator has already eliminated the carrier, a transmitter only needs to pass the resulting double sideband suppressed carrier signal through a highly selective band pass filter like a quartz crystal ladder filter. The filter strips away one of the sidebands, leaving a pure, highly efficient single sideband signal to be amplified and transmitted. Common circuit designs. Diode ring mixer, the most classic and robust design, using 4 matched diodes arranged in a ring and 2 center tapped transformers. It is passive, bidirectional, and handles wide dynamic ranges well. Active integrated circuit mixers. Integrated circuits like the NE602, SA612 or MC1496 use internal cross-coupled differential amplifiers, a Gilbert cell, to achieve modulation with fewer external components while also providing signal gain. FET transistor modulators, using matched field effect transistors or bipolar transistors to actively switch the carrier on and off at the audio rate. A little more detail about diode ring mixer, which is the commonest in usual homebrew circuits. A diode ring mixer, often called a double balanced mixer, is a purely passive circuit that mathematically multiplies two signals. It is the workhorse of radio frequency design because it inherently suppresses both the original carrier wave and the modulated audio, leaving only the desired sidebands. The classic diode ring mixer consists of only 3 components: input transformer T1, an RF transformer with a center tapped secondary winding, output transformer T2, an RF transformer with a center tapped primary winding. The diode ring, 4 identically matched diodes usually Schottky diodes for fast switching, connected in a continuous circle, anode to cathode, all the way around. The carrier signal is injected into the primary winding of T1. The modulating audio is applied between the center tap of T1 and the center tap of T2. Output signal, that is the double sideband suppressed carrier, is taken from the secondary winding of T2. Unlike standard amplifiers where signals remain analog and linear, the carrier signal in a diode ring mixer is fed at a very high power level. Its job is